Evaluate the indefinite integral of dx over 2 plus 9x squared. So, a couple of things you want to notice. Outside of the lesson, it's a lot different when you're having to do these all by yourself. You have 1,000 techniques and you're trying to figure out which one of those techniques you're supposed to apply. So you have an x squared that's on the denominator, and on the top, the degree is basically a 0. Okay, so the difference of those degrees is a 2. This means that we're going to do an arctangent. Well, we just came up with a rule for this one where this is our a squared. So a squared is equal to 2, meaning that a is equal to the square root of 2. Okay, and then also this 9x squared is equal to u squared. 9x squared is equal to, there we go. And then take its square root just like we did before, so u is equal to 3x. And now we're good to go to just plug this into our antiderivative rule. So the antiderivative here should be 1 over a, so it's 1 over the square root of a. Don't even worry about fixing it. Well, you probably should put a 2 there instead of an a. Leave it like that. Arctangent of u over a. And our u is 3x, and our a is the square root of 2. Again, don't worry about fixing it. And by fixing it, I mean rationalizing it. You can leave it just like that. It's perfectly okay. And it's done. All right, so just for example, if you don't remember, like you had to do this on the AP exam and you didn't remember the technique, then the idea is to turn that into the a direct application of the derivative rule, which looks like this, dx. Then you have a 2 plus 9x squared. You divide everything by 2, divide by 2, divide by 2, right? And then you would turn this into 1/2 definite integral dx 1 plus, and then inside the parentheses here, when you pull out that square, it's actually a 3x over the square root of 2 squared, and then you can just do the u substitution like we normally did. But you're going to get the same exact thing that we have over here. All right. That being said, next up we just have a recap of completing the square, because often what happens on this, like the one that we just looked at, we didn't have to complete the square. It is all very obvious to us, but we may have to complete the square in order to make the antiderivative rule for either arcsine or arctangent happen for us, and that's what's going to happen here on example 11. Again, notice that we have a square on the bottom and the degree of the top is essentially a 0. A clue that we should try to complete the square on this quadratic so that we can force in the situation where we have arctangent. Let's take a look then. So to complete the square on this denominator here, you just do it on the two variable terms, x squared minus 4x plus a blank, minus that same blank, and then plus 7. All right, and then what number completes the square here? You take half of the middle term. It's a -2, which you're going to square, and that's going to be a 4. We don't have a leading coefficient out here other than a 1, so what I added inside the brackets is what I've got to subtract on the outside of the brackets. Okay, so that means that the completion of the square would be an x minus 2 quantity squared. Combining those constants up, we get a 3. All right, so let's rewrite our integral here, so we can make it match up with the antiderivative rule. So we've got antiderivative of a dx over 3, I will write as our a squared, plus x minus 2 quantity squared. All right, remember, this 3 here is a squared. So a is equal to the square root of 3. And then the x minus 2 squared is your u squared. And your d, whoops, not your du, your u squared is equal to an x minus 2. Well, no, come on, really. Yeah. All right, now we just throw everything into our antiderivative rule, and we would have 1 over a, so it's 1 over the square root of 3, times the arctangent of u over a. Our u is x minus 3. No, it is not. It's x minus 2 over the square root of 3. And then once again, You can leave those square roots on the bottom. It's perfectly acceptable unless your answer key, your like multiple choice, rationalizes it. But I'm highly doubtful that that's the case. I'm just going to leave it like that and be done with it. All right, so we have probably one more example. It's probably the most complex of the bunch. I'm going to take a look at that in the next video.